Hello, so this is our first lecture after midterm. So before midterm, we studied about the manipulators and especially 2D manipulators, meaning that the manipulators with one joint or two joints uh, and maybe three joints, but they are restricted to move in a planar space x and y. And we have not studied the 3D mobile manipulators which can move in 3D space. We will cover it later. So today we'll start the next part of this course, which is mobile robots. So the example of mobile robots you very well known to you, that any vehicle which can move on the wheels, which has wheels. For example, you work in your labs on Arduino Arduino robot. So that is example of the wheel robots. So meaning that any robot which can use wheels to move from one place to the other place, right? Manipulators, you have basic introduction of this already, that which has the links and joints, but its base is fixed at one place. Let me open this one. So its base is fixed at one place, so it cannot move from one place to the other place, right? So this is like fixed over here. Then the other type is the legged robots. Legged robots means that the robots which can walk on the legs. So like humanoid robot is one example, and there's quadruped quadruped robots which can have move on the legs, maybe two legs or three legs or four legs or six legs. So they are the example of the legged robots. Then aerial robots which can fly. So this can be quadrotors, or can be any number of rotors it can have, or even a fixed wing uh, drones. They are all come under the category of flying robots. So our focus today will be on mobile robots, meaning that which can mobile robots which can work on move on wheels. Especially in this class, we will study the only wheeled mobile robots, but let we have a basic introduction of the mobile robots in general. So mobile robots can, depending on the type of the locomotion. Locomotion means that the type of the motion they have. They can travel on the ground or the surface of the water, or maybe underwater or in air. We have seen that this is in contrast to the fixed base manipulators, which are also robots, but their base is fixed at one place. They cannot move from one place to the other place unless they have some they are put on some mobile robot. So that is another type of the mobile robots, that we have the mobile robot and then we fix a manipulator on top of it. So that is called the mobile manipulator. So mobile robots are less structures, meaning that because they are not fixed on one place, so it is hard for the mobile robots to find their location, position, orientation, and similarly the orientation and position of other spaces in the environment, as contrast to the mobile fixed base manipulators, which are fixed on one place, so they know that what is their zero position, and with respect to that fixed base, they can calculate their, using forward kinematics, inverse kinematics, they can calculate the position of each joint and the position of the end effector. And usually when we use the manipulators in industry, so the workspace is very well structured, meaning that the position and orientation of the objects which they have manipulators have to work with, they are placed at some specific locations, known locations. But this is not the case in case of the mobile robots, because the mobile robots have to move in their workspace. So and the workspace may not be static, meaning that the objects in the workspace, they may be moving as well, and the position of the objects may not be fixed in one place. So the example is that uh, driverless car, self-driving car. So self-driving car is a mobile robot. So you see the environment of of a road. So everything is moving. There is very less things which are static. So people are moving, vehicles are moving, and the this self-driving car, the robot itself is moving. So everything is dynamic. So to get the real-time position and orientation of the robot itself and the environment around it is very difficult. So this means the less structured environment. So manipulator versus ground mobile robot. So we have talked about this, that the manipulators, they operate in a constrained workspace and they know their absolute positions and itself, and also the most of the time its workplace as well, workspace as well, and they may not be use sensors to perceive their environment because the environment is fixed. But in case of the mobile robots, they work in unknown environment or unconstrained environment. They need some external sensors to get the perception of their environment, and also they need to know their own position, and to interact with the external environment, they need some sensors to avoid the obstacles and so on, and navigate in their environment. We can combine this, let's say we say 1 and 2 second type in a third type, which is let's say 1 plus 2. So meaning that we can combine the mobile robots and manipulators in the third category, which is called the mobile manipulators. So in this case, for example, in this case we have a mobile base over here, mobile robot here, and then let's I call it MR, mobile robot, and then on top of it we fix a arm robot. So this way the base is moving. The base of the arm robot is not fixed in the environment, but it is fixed on the mobile robot, but it is not fixed in the environment. So mobile robot is moving in the environment, for example, the factory floor, like Amazon warehouse, for example. This kind of robots are deployed to move around in the big warehouses and to manipulate the objects. So in mobile robots, when we talk about the mobile robots, so that is more difficult discipline as compared to the manipulators, right? As we mentioned that manipulators are work in the structured environment, but the mobile robots work in the unstructured environment. So there are some basic questions which related to the mobile robots. For example, this first one, where am I? So where am I means that what is the current location of the robot, right? We have to figure out the current location of mobile robot. This is the first thing, because without knowing its own current location, the robot cannot go to the let's say it cannot cannot go from point A to point B, or it cannot to reach to some other objects to grab it. So that is the first question it has to solve. So this is knowing the current location of the mobile robot is called the localization task. So in mobile robots, the localization task is module is a one full-fledged um, the module which um, have to make to move the successful operation, to move the mobile robot in its environment and perform the successful task. The second type of the question which mobile robots have to solve, where am I going? So this is about the um, where am I going means that what this is about the path planning, right? So we have discussed one type of the path planning, or moving from point A to point B, like bugs algorithms, but we'll cover more later. So this talk about the path planning or trajectory planning. So where I can go from point A to point B. So how do I get there? So this is the uh, control and motion planning, that how I move from point A, for example, and then there is a point B in the environment, and mobile robot is, let's say, it is present on current location A with these wheels, for example. So then its task is to, if there are obstacles in the environment, so how how it figure out that how it can go without hitting the obstacles, and without stucking in between the obstacles, how I can reach to the destination point. So this, to perform this kind of the tasks, so the robot have to figure out it had different options, but maybe this path is not, this space is not enough to move in between, and maybe try to figure out over here, but it cannot go from here, and maybe somehow it can manage to go from here to this, like this. So this is the path planning and how to move between these points. So if you split this path in different points, then the motion planning algorithm, or way how I do how I get there. So this will move robot from point A to point B in these segments. So mobile robots is very multidisciplinary area. So robotics in general actually multidisciplinary, but the mobile robots is the type of the robotics, so that is also multidisciplinary. So there are many areas, many technologies which are used in mobile robots. For example, first one is the locomotion. This is the design of the robot design. So robot design is one of the big area in the robotics. So how we design this robot? So this is the mechanical structure of this robot. So the people who have the background from the mechanical engineering, mechatronics, they are good in this type of the sub area of the mobile robot. Second is perception. So how it can see the environment, right? Or perceive the environment, or uh, you can say the see its environment. See and understand, right? See and understand. So that is the perception part. So people who have the background from the image processing, computer vision, sensors, signals, they are very good to work in this sub area of the mobile robots. The third major area is the navigation. So this is the algorithms mostly. So it is the algorithms. So it means that the people who have the background from the computer science, or the data science, information theory, the people who have this kind of background, they can work well in this sub area of the mobile robots. So mobile robots is very multidisciplinary the area, and it is growing rapidly, especially with the advent of the coming of the AI. So AI and mobile robots, they are merging together to produce some intelligent robots nowadays. So what are the major components of a mobile robot? So as we said that the mobile robot is not a uh, single area; it is a multidisciplinary area field of study and work. So both hardware and software components are involved to make a full system of the mobile robot. So locomotion means that how the robot can move from point A to point B, or how it can move through its environment. And the sensing part, sensors, they can uh, determine the for example the position, velocity, of the robot itself, and also they can perceive the environment, like location of the objects in its environment. Reasoning or decision making, that decision making meaning that the robot can get the information from its sensors, and then it can, through some algorithms, it can convert this sensing measurements to the actions which it should take. Control. So control engineering means that the control in robotics, mobile robots, means that how it can do the motion planning, how can execute those actions which it need to take in its environment. And communication is maybe optional part of it, but as a complete system, the mobile robot should be able to communicate with its operators or outside world. Let's talk about these components a little bit. So first part is the locomotion, right? So locomotion is a process of causing a mobile robot to move. So how we can move the mobile robots? There are many options, right? Many options that we can attach wheels to the mobile robot, we can attach the legs to the mobile robot, or maybe the tracks to the mobile robot, or maybe combination of these different types of the mechanisms. So this is the called the locomotion in the mobile robots. So basically, how we can produce the motion or torque, so to move move this mobile base which we have designed in the that we have designed some mobile base with through some mechanical knowledge, and now we want to add some electronics and want to move it from one in its environment. So for that, basically we need to attach this locomotion. So there are different options, as I said, that depending on our tasks in hand, for which application we are designing our mobile robot. So it depends on what type of the locomotion we should add. So if we want to just move uh, uh, on like uh, what is our application? So it is our mobile robot should move, walk, or jump, should run, slide, scat, swim, fly. So there are different options, right? Depending on the what type of the motion we want to create, depending on our application. So in nature, we found that different kind of the locomotion. Already we see the most common is walking. Like every day we walk. So this walking has like the legged robots in the mechanical systems, and similarly running and jumping. So in nature, this is very common also in this, especially in the animals. So this can be emulated with the leg motion, how we create the legs which can have the springs, for example, and the if we apply the forces, so we can jump or hop. Sliding motion in nature is also like in the snakes, they move from one place to the other place by sliding on the ground. So this can be represented by a sign like of the motion, and we can create this some robot which can produce this kind of motion and slide on the ground. Then the crawling is represented by this spring which contract and expand, and people have created this kind of robots which can use this kind of locomotion. And wheel locomotion, of course, is the biggest or most common in human made system, but not in nature, right? In nature, we couldn't find any wheel based locomotion. But in human created systems, we find the wheel based locomotion is most common. So depending on what type of the locomotion we have designed for our robot, so uh, we can uh, we can figure out that the stability of the locomotion of our system depend on the how number of contact point with the ground we have. For example, when we talk about the wheel, so wheel has only one contact point on the ground at a time, right? And then we have the center of gravity of our system for stability calculation, and then the the type of the terrain, or the type of the environment or inclination in which our robotic system is operating. These are the factors which determine the stability of our overall system. The second thing is that the what type of the contact we have with the ground. So our contact area determine the friction between uh, our robot and the ground. More friction we have, so more easy we can move on the ground. So if friction we have zero friction, so it is hard to move on the ground. Angle of contact and friction. So these are the characteristics of the contact with the ground with our locomotion system. For example, wheel. So if I draw like wheel over here, right, we see that there is a ideally there is one point of contact over here with the ground, right. So more this contact is strong, and more stable our motion will be. And of course the our the locomotion also depend on the structure of the environment, and the type of the environment. It is a soft or hard surface. So these are all the factors which we should be taken into account when we design the locomotion of our system, of our mobile robot. So land-based mobile robots usually, as we talked about, that they can use the wheels, they can use the legs, tracked or hybrid. So tracked means that this kind of the tank-like locomotion tank. So we have this kind of the chain, and then the wheels. So the chain cover all the wheels. So this kind of the locomotion, you see that we can have the more contact with the ground. The contact surface increases, and we have the more stability and more less slippage on the ground. So this kind of the uh, the track system, track locomotion, it we can operate on the soft surface, we can operate on the slippery surface. But if we have only the wheels, one single wheel, so that is hard to operate on this kind of surfaces. So depending on the application, we can choose to use the wheeled locomotion, legged locomotion, tracked, or maybe combination of all, combination of different locomotion systems to design our mobile robot. So, but in most common system which we create, they have the wheeled locomotion. So wheels, in addition to being simple, this is a very simple design that and very readily available and very cheap type of the locomotion, and they are very good suited for the on this flat surfaces, right. You know, but you know the if surfaces like have many ups and downs, maybe the stones or maybe rubbles. So a wheel locomotion is very inefficient in that case. But on flat surfaces, it is very efficient, like on the roads, right? So if we have these flat road surface, so then the wheel locomotion is very fast, very efficient, and most of the depending on our application, if we are designing our mobile robot to work on the to move on the road, for example, the driverless car, so then wheel locomotion is the best option. But you know that the legged locomotion will not be efficient on the road. But the legged locomotion is more efficient on the uneven surfaces, where we have the, for example, um, rugged uneven surface, and we our wheels cannot roll on that surface. In that case, the legged locomotion is more efficient. So our mobile robot, it can be a quadruped. For example, we have four legs, and then it can, using the legs, it can move in that environment which is uneven or which has not a flat surface. but as the the surface becomes more soft, so wheel locomotion accumulates inefficiencies due to rolling friction, but the legged motion suffers much less because it consists of only one point of contact. So this is like we already talked about that. Depending on the type of the surface we are designing our robots to work on, we can choose wheeled locomotion or legged locomotion. So in this class, we are mainly concerned about the wheeled locomotion and land-based mobile robots. As this kind of robots you already have worked on, like we have 4 wheels or maybe 2 wheels, uh, and you control this kind of wheeled robot with some kind of the um, microcontroller like Arduino or some other. So this we already have done in your labs. Okay, this is the same that we have talked already, that what are the benefits of the um, wheeled wheeled robots, and what are the what are the limitations and what are the disadvantages as compared to legged motion locomotion. So you can read it later. So let's talk about the um, kinematics of mobile robots. As we discussed for the we also studied this for our 2D manipulators, right? You remember that we studied the forward kinematics, inverse kinematics, and then forward differential kinematic, inverse differential kinematic for 2D manipulators. Now we'll do some we'll study some kinematic models for mobile robots. So like forward differential kinematics, inverse differential kinematics for our mobile robots, we'll try to we'll cover these topics in this class. So why we need the kinematic models? This is the need of a mathematical model. Where we derive it. So this is the first thing that whenever we want to design some the dynamic system, we have to create the mathematical models to understand the behavior of the system and design the system. This is the first step, right? And second reason is that we have to design the controllers, navigation systems, and adjust some parameters of the actual systems. So we simulate all these scenarios in terms of the mathematical model before going to a real system. This is the degree of freedom definition for the mobile robot. So there are a minimum number of variables to describe the system. Like in uh, in planar arm robots, we see that the how many degree of freedom it has. So it has the 2 degree of freedom in that case. But if we have the planar mobile robot, for example, we have this mobile robot which can move on this, let's say this caster wheel, which can move in a 2D environment. So what do you think, how many degree of freedom it has? So in this case it has x and y position, right? And also it has some rotation. So in this case we can describe the full motion of this planar 2D mobile robot with 3 parameters, x, y, and theta, because it not only move in the x and y uh, plane, but also rotate in the x and y plane about the z axis. So theta about the z axis, right? So if we have like if we say that this robot has its own, this one. So this is like its own x axis, y axis, and then z axis on the top. So we call x r, y r. Similarly, we can say the x world and y world. This is the world frame, this is local frame. So it can rotate about the z axis of the local frame. So that will give you the angular velocity, or the angle with respect to the world frame. So this is the degree of freedom in this case. If we have the like flying robot, which can fly in air, for example a drone. So in this case, how many degree of freedom will be? It has one rotor over here, one rotor over here, one rotor over here. So in this case, because this is the moving in 3D space, you can say x world, y world, and z world. So this is moving in the 3D world space. So it means that um, and its own, let's say its own frame, this x, y, and z. We can say xr, yr, and zr. So it has how many degree of freedom it has? So of course we can describe this system with a full system which is in 3D space with position and orientation. Position in this case is 3D. We have x, y, and z position, and also it has the roll angle, that we call it whatever we can say this roll angle, pitch angle, let's say we call it whatever this one, pitch angle, and yaw angle, let's say theta and then yaw, like this. So it has 6 parameters which will describe the, so this system motion. So it has 6 degree of freedom, right? So this is the roll is the rotation about the x axis, rotation about the y axis, rotation about the z axis, roll, pitch, and yaw. So this way we can determine the degree of freedom of our mobile robot. Okay, so any question? You can type your question because I cannot hear you. I'm using this. I'm not using the headset. I'm just using the mic. So you can type your question if you have. Okay. Sorry for that.